So we can start. We'll talk about hypernetworks. So let's start from hypernetworks. In general, when we have a classical neural network and we would like to minimize our cost function and we have some classification task, everything is quite easy. We know how to choose the architecture, we know how to choose the cost functions, we know how to find minimum of the cost function according to the parameters like and or NeRF. And in this case, everything is solved. We don't have anything. But we can think about the training process in different way. We have two architectures. The first one is hypernetwork, and the hypernetwork is trained directly by gradient descent. And we have the target network, which is not trained directly, but hypernetwork produces weights to the target network, and target network get weights directly without any training. And in general, change all the process, because when we update parameters of hypernetworks, we move parameters only by a small change, like in gradient descent or some other modification. But the weight of target network can change drastically, because when you produce small change in each parameters of hypernetwork, target network can produce completely different architectures. So, in practice, our target network is not trained directly, but get the weight from the hypernetwork. Okay. And it occurs that hypernetworks are able to.
Maybe I have one question. Yeah, I have one question. So, I like the definition, but is it correct, my understanding, then essentially a hypernetwork generates another network?
Yeah, but in our framework, we generate only weights.
The weights of the other network. The architecture is predefined. Okay.
Of course, we can change this paradigm and produce different architecture here, but I don't do my works.
Mm-hmm.
Okay. And in general, in my work, I produce a lot of papers, algorithms with hypernetworks, hypercolor, hypermam, hypershot, and other hyper modifications. If you are interested in working with hypernetworks, I always open. Okay, so if we know what is hypernetworks, we should to define what is implicit representation or continuous representation or something like that. So in general, when you have some discrete data, for example, it is described by a vector of numbers. Yeah? We have some resolution, for example, 1000 per 1000 pixels with color. And in implicit representation, we train the neural network, which encodes the shape, color, and structure of the image in the neural network weights. And in general, for the index of the pixel, y, for example, the third pixel or horizon, we neural network trying to reproduce the color attribute. So everything is inside the weights of the neural network. Why we want to do it? Because thanks to this representation, we obtain some features. For example, we are able to produce high resolution, so we can ask our neural network for more pixels than the original image and obtain the higher resolution. We can ask our neural network for picture out of the image and produce some elements which are next to the original picture. And of course, implicit representation is quite general. We can encode 3D objects, 3D point clouds, videos, sounds, and images in implicit representation. Okay, so I would like to say a few words about about generative models, 3D objects, implicit representation, and hypernetworks. Everything was started from this paper, which is authored by Tomek and Maciek, thanks to this paper, everything was started with the object in my case. And in general, we produce the autoencoder. To the autoencoder, we put the point clouds, and at the output of the autoencoder, we have the point cloud also. So this architecture is quite complicated because point clouds are invariant to rotation and permutation. So we should to use some neural network here, which is called point.net, to process the point. And the problem is here because our generator must return the fixed number of points. So if we train our neural network by 2,000 of points, we can produce only object with 2,000 of points. This is a problem because it's sparse. When you produce some object which has 10,000 of points, you see a lot of empty spaces. So this is a problem with output of the network. So we decided to use hypernetwork paradigm. So encoder is exactly the same as before, and the decoder produces weights target network, which works element-wise. So for each 3D point, returns one 3D point. And when you want to reproduce the full object, you need to run this target network as many times as you want. And in general, it is nice because you train your model only on element with fixed number of points, 2,000 or something like that. And in inference time, you can run your target network as many times as you need and produce any number of points in the object. Of course, it occurs that similar approaches was constructed by conditional mechanism instead of hypernetworks. It was point flow, but our network has some more features. In general, it occurs that when you have your target network, it is trained that you transform invariant distribution of the ball to the distribution of point on the surface of the 3D object. So if each point from the ball goes to the surface of the object, so the bounding sphere of this element goes to the bounding of the 3D object, and you are able to produce the mesh. So we only in inference time, after training, without any change, we are able to propagate the sphere, triangulation of the sphere, the mesh, and obtain the mesh of the object. And it is quite nice because most of the existing methods produce points or meshes, or must be trained on points and meshes. We train only on point clouds and produce meshes additionally. And it occurs that it was a nice architecture. It appears in ICML 2020, and this autoencoder-based architecture, so you can produce some interpolation. Everything works. It's okay. So after this model, we try to modify it, and we will change something in target network here. In general, here we want to put a flow model. You know what is flow model? Okay, so flow model is quite easy to describe. We have GANs when we have generator and discriminator, and they fight each other to produce some shape element. You have autoencoder when you have input, and input should be as close as possible to the output. In the center, you force to be a Gaussian, and flow is exactly the same, but the encoder and decoder is the same function, but the decoder is the inverse of the encoder. And in general, you are not able to change the size. So if you have 2,000 elements here, you also need to have 2,000 elements, so the shape is not changing, because if you want to produce inverse function, you should be able to you should have the same dimension. And in general, the Jacobian of the transformation is trivial or easy to calculate, because in this model you are able to calculate the log likelihood of the data directly. it's not very important, but in general, there exists FF architecture, which is this kind of flow, this continual normalizing flow. So in general, you find a continual transformation from the Gaussian distribution to the distribution of data. And in general, it is parameterized by some differential equation. And in general, you should to give the dynamic function, and you are able to model the transformation. This transformation is invertible because you can integrate from 0 to 1 and from 1 to 0, and it works perfectly. So we put the continual normalizing flow here. It occurs that if you want to use normalizing flow, your distribution cannot be 0 anywhere because you are not able to calculate the log likelihood, because log likelihood from 0 is logarithm from 0 and is infinity. So it is not possible to use here universal distribution on the ball. Why we need to? Why we want to use continuous normalizing flow? Because there exist many models in this time which claim that flows are better for 3D object or surface of the 3D object than classical neural network. So we decide to produce some new distribution which has this property that is no 0 anywhere and has the empty space inside, and we call it log normal distribution with the parameter which say that how the size of the distribution is. We start to train from the size sigma, so it is quite blurry, and during training we go to the distribution which looks like the sphere in 3D object. Of course, this distribution don't have any 0 elements everywhere, but it is a very small number opposite the. Thanks to this modification, we was able to produce the flow model, and thanks to it, we are able to model the transformation from the uniform sphere to the final object. So in practice, we can start from here and integrate it to each point of this model. So we are able to see how model transform the sphere to the object directly, and it is continuous. So the transformation is quite nice. We compare our model with some other models which use flows, and most of them use Gaussian distribution. And when you use Gaussian distribution, your transformation is quite complicated because the center of the Gaussian goes to the different parts of the elements. So if we use the log normal distribution, it is quite easy to see that your model do not any changes. So if points are close each other on the input to the flow, they are close to the output of the flow. So our model is able to model the shape of the sphere in natural way or something. Okay, so these two models, this model was also published in PAMI, so it was very nice. So it occurs that we are able to produce our 3D object with point clouds and meshes very nice. So we start to thinking what next? And next step is to generate some object and put inside some stand. So for example, you have some room and you want to put here some chair. And when you scan the flat of something, you obtain some part of the chair. You don't have everything in the chair. So we start to producing some algorithm which take the existing part of the chair, room, so some environment, and we would like to produce some chair here. And we try to do it in a generative way. So this is existing part, and we can produce this kind of chair, but it should be corrected with the existing part. So this is the goal of our project. And the synthetic part, it works that we have a part of some 3D object, and our generative model produce some missing part. And as we can see, our model is able to produce different of cars, head, background, or something like that. So it is really generative. And you know, everything is okay, but our model is not connected to the environment. So when we produce some chair which is corrected with this part, and we don't know how legs are, how long the, we don't have any information about legs, so our model is able to produce too long legs or too short legs. So we try to construct some model which will be able to suit the 3D object to the environment. It was quite easy. We produce some adversarial attacks to the existing object to be according to some cost function connected with the environment. Here we say that the constraint is the distance to the floor. And when we change the input to the neural network to be as close as possible to the floor, it is able to produce of the model. So how the model works, it's quite easy. We have autoencoder. On the first part of the encoder, we put the existing parts. In the training, we have 2 parts. In inference time, we have only 1. So the missing part, which is known in the training, goes to the encoder. We concatenate the representation, and it goes by decoder and produces the target network. And you know, these parts are completely different, so they encoded different representation, but they are concatenate or mixed in the target network ways, what makes the model or force the model to construct the correct representation of the object. In inference time, okay. In inference time, here we force the line to be as close as possible. We sample this point here and get the representation of the existing part, and then produce different missing objects. Okay, and it was also quite a nice published conference. Okay, so it is nice. We are able to produce 3D shapes, point clouds, meshes, and we are able to produce missing parts or produce the element which is correct with your environment in some sense. So we start to thinking what next, and it occurs that exists many different representations of objects: 3D point clouds, voxels, meshes. So we start to think about voxels. Maybe it is possible to put it in our framework. And it occurs that people find out that construct the SDF. And it is nice because it was quite close to our model, and in similar way it was producing similar way. In general, you have the point inside the object and the point outside the object, and the surface of the object is a classification boundary, which is produced by a neural network which discriminate inside from outside. So we decide that in target network we use fully connected layer, fully connected neural network. We use slow model, so it is able to produce to use classifying. So as the other. Of course, there exists some solution which takes the coordinates of the point which we want to produce and the feature representation that people concatenate. We produce the hypernetwork architecture. It will exactly the same as before, but here is the classifier, and it works nice. But in practice, occurs that we produce some empty elements, and in the result of the neural network. So we decide that this is a problem because when you have small points and the classifier produces the boundary and you don't have enough points, it is able to move the boundary a little bit and something disappears. So we decide that we should propagate not only point, but voxels, so the 3D cubes. And we use interval arithmetic. So here we use interval arithmetic. So the neural network which propagates the square or hypercube. Hypercube, in practice, 3D cube. Yeah. So how it works? It works by interval arithmetic. So it is possible to modify the neural network in such a way that we propagate not only the inside element of the square, but the full square. So the square of the linear transformation is a linear transformation of the square. So it is only this modification. After that, we apply ReLU activation function. So take only the positive parts. And and this is also the square. So you can do it again, and it is quite easy to implement. And the cost function works in this way that not only the point should be on the correct side of the classical boundary, but the full square or something what was produced by the input square on the correct side of the. So the point has some value. And thanks to this modification, we was able to solve the problem with solve the problem with empty elements. Okay, so it was nice. Everything is okay. We are able to cross point clouds, voxels, and meshes. So it occurs that people start producing 3D object by patches, because with all previous models is the problem that you produce something from the sphere. So you have the same number of holes with the elements you transfer and you produce. So when you produce a chair and the chair has some space, I don't know, in the bag or something like this, you are not able to produce it. So people construct something what is called Atlas. Atlas is a general neural network which produces fixed number of patches which should be transformed into patches on the surface. And everything is okay, but you are not have any mechanism to fill the missing elements, because when you fix the number of patches, it's a problem. So we decided we can produce it by hypernetworks, and as we know, hypernetworks are able to produce as many points as we need, so we can produce as many patches as we need. And the modification is that we call it locally conditional Atlas. You can produce as many patches as you need, so you can fill all the missing parts. And it works in the similar way as before. The first stage is the same as hypercloud, and we add additional target network which transfer patch in similar way. It occurs that everything is okay. We are able to produce. Atlas and the classical solution have some artifacts in empty space, and we are able to produce coherent topology or something. Of course, the model is quite problematic, and our reviewers it is a problem for reviewers, so we still work with that. To produce the full object, we need 400 patches, and this is quite a lot, because the classical solution has only 15 or something like that patches, but we are able to fill all empty space. Okay, and this is the end of producing the shape. And when we finish the producing a shape, it starts to fight with colors. Yeah. So what with colors? It is quite problematic, because when you are able to produce the shape, it is quite hard to use in practice application, because you need the color. So we try to add the colors by our model, and we do it also by hypernetworks. And it works very easy. So the first part, encode the shape, is exactly the same architecture we showed before. And we produce the new patch or new part, which transfer the shape with colors and produce only colors. But the first part is able to describe the shape. So when we add the second part, neural network gets the shape and the input, but it is not. But neural networks don't want to duplicate this information. So from this element, take only the color. And in this way, we produce the point cloud with color, which works quite well. But we need to produce the mesh with color. So the mesh can be produced in the similar way as we produced before. And when we produce the mesh and the node of the mesh has colors, we produce linear interpolation between nodes. Thanks to it, we produce the color on on faces. And we obtain something like, and maybe it is hard to agree, but it was thought 2 years ago. So people will produce this kind of colors. Of course, we have a lot of problem with the sharp change of the color on the window of the car, because we have linear interpolation in space, so it is quite hard to produce the sharp connection with colors. And it is a problematic, because we don't have any idea how to correct this architecture. But it occurs, but it occurs that some guy find out that exists NeRF or produce the NeRF. It occurs that NeRF perfectly suits for our architecture. Yeah, because we can add the NeRF to the hypernetwork architecture. So if you are not able to solve your problem, you can wait and the world can solve the problem for you. So what is NeRF? Who knows what is NeRF? Okay, so I describe in a few words. So in general, the NeRF architecture take few existing images of the 3D object with a given position. So you make few images, and the network should have information of the image of the camera. And our neural network produces the 3D object, but in this way that produce novel views. So if you say that you want to produce your object from some position of the camera, the neural network give you what you should see. So in general, in the game, when you become car, and for example in GTA you want to destroy this car, you see only the one view from the one side, but the car exists fully because some guy construct the 3D mesh and it exists with any side. And in NeRF architecture, when you look at this car, it exists only from the point of view from your point of view. The car is not existing in every position because the structure of the 3D object is encoded in the neural network. Architecture and the description of the model is quite easy. We have few images with known position camera. In training, you produce the array, which goes across some existing pixel with known color. So the color is your target, and on the array you sample some point. For each point, your NeRF produce 4 elements, RGB colors of the color of this point, and sigma is the existence of the point because some point doesn't exist. And you aggregate or sum element across the array, and you should the sum of this value on the array should give you this color. And you train in this way. The arrays are crossing, so the representation should be correct from different sides. And in inference time, I know that this is the same image, but we can think that this is a white card, and we want to produce the new view. So it goes to each pixel, you produce the array, sample point on the array, your architecture of NeRF model give you these colors, you aggregate these elements and sum these elements, and it gives you this color. Because you train in this way that sum should be as close as possible to these elements, so in inference time it's the same, and you produce this image. And it is a NeRF, so it's quite important. The shape, color, structure, or something like that is encoded in the neural network weights. Similar to this example which I showed the first of the slides. So everything in the neural network weights. When you want to see your 3D object, you ask your neural network to produce your new view pixel by pixel. Okay, so the first idea to use is to produce the same model as we produce for flows, fully connected intervals, and etc. So the idea is maybe to put something to the encoder and obtain something And the output of our architecture should be NeRF, because the neural network weights, which produce you a new view of them. And it is problematic because we don't know what to use for the input to the encoder. First, we tried to use only one image, but it was not enough. Then we tried to put all the images we have, but it is quite hard because it started to training, I don't know, 10 days, and we have only one app. So it was problematic. So we decided that we put here the 3D point cloud with colors. Yeah, and this point cloud goes here, and we hope that the coder is able to produce neural network which produce the new views instead of. It occurs that it works in IDEAS. You put the autoencoder 3D point cloud with colors and obtain NeRF representation, which is able. And as you can see, the result is better than before, but still the shape of the windows or lamp, every place where the change of the color is sharp, is in some sense blurry. And you know, what is the problem? We don't know what is the problem. First, we start to thinking that the problem is that point cloud is on the input to our NeRF. Then we start to thinking that the problem is with the NeRF architecture. But at the end, we decide that the problem is with autoencoder, because most of autoencoders produce images. So we, some elements produce. So we decide to change it to the GAN. And the architecture of the GAN is quite similar to the previous architecture. From the noise, we produce the waves to the NeRF model, and the NeRF model produces only one randomly selected view. So NeRF produces only one 2D view. And this image goes to the discriminator, which is dedicated to the images. But you know, because thanks to this generator, try to construct some view which is sharp. But you know, because NeRF produces all possible views, it is quite hard for the neural network to produce, I don't know, from front view red car and from different views, I don't know. So thanks to the ability to NeRF to produce the coherent at the same models, it works nice by using dedicated only for.
Sorry, one question. What activation do you use in the NeRF?
NeRF is exactly the same as in the original architecture. So
ReLUs,
yes, and of course it works that here is the position of the point and the camera, and
that's clear. I just want and in your autoencoder or your variation or your autoencoder in the previous approach, what activate?
ReL.
Also ReLUs.
Everything everywhere was ReL. Okay, and it occurs that it works, and I don't know, the shape which we produce are quite sharp, and you know, the windows are transparent in general. So we decided that this model produced very nice 3D object. And the question is what next? Because we decided the generative model works maybe not perfectly, but this can be used in practice. So we decided the next step is to add some I don't know, possibility to change the object. Yeah, because when you produce some object, you know, it is fixed. It is not able to, I don't know, start to drive in this car. Yeah. So we decided that the best way to start it is to start with human faces. Yeah, because human faces are very, very nice to parameterize, and we find that exists some model which is called Flame. It's quite simple architecture. You have 42 parameters. When you change these parameters, your face start to moving. I'm not sure we have. Everything's okay. So, and this model don't use any color. So when I move some factors, I can change the the face. And such model is quite well built and very often used for games or something like that to produce avatars. So we decided that we try to add NeRF renders for mesh representation. So mix the implicit and explicit representation. So we have the mesh, which is easy to move because you take some 3D point clouds and the 3D point clouds or the nodes of the mesh in space, and add the neural network to produce the color and a novel view of this object. So now our model works in this way that neural network, so NeRF produces RGB color, but the sigma existence of the pixels is directly given by the distance of the mesh. So the neural network is able to give the color only for pixels which is close to the mesh. Thanks to it, we connect mesh with colors, and thanks to it, we are able to train our model only on the fixed phase in the 0 position. And when you finish the training, you can start to moving the head of the mouse, similar in Flame, because when you move your mesh, your neural network produces the color in the different positions. And thanks to it, we obtained a manipulation of the. In practice, we have a little bit low quality of this model, and reviewers force us to modify it, and we work with that. So now we are able to produce this model. We are able to give the life of this model, but the quality of the model is not very high. So we thought,
where was it submitted?
ECCV. Yes. And everything was okay, but one of the reviewers says, it is not sharp enough. And after that, other reviewers say, the sharp is not enough. Yeah. So about
the problem already.
No, we are in progress, and now 3 people independently try to solve this problem because we know where the problem is. In general, the problem is with computer graphics, because when you calculate the distance of the point to the mesh, the PyTorch models give you the distance to the closest face. But we need to find the closest face on the right. So something like ray tracing. It occurs that no one in PyTorch implements ray tracing, and we try to implement ray tracing in PyTorch. If we finish it, I believe that everything will be solved, but 3 students, unfortunately not PhD, but normal master's degree students try to do it independently. I hope some of them finished. But we are very close. Okay, and the last model is that we start to thinking about what is the problem of NeRF and how to solve it. And in general, the problem of NeRF is that everything is in the neural network weights. And it is not suited for 3D objects. So people try to change it. For example, use voxels. So we have trainable voxels which change some part of information or keep the same some part of information on the 3D object. And here we have 3D geometry, so better. Some people decide to use 3 planes. So we have 3 planes, which are in this way. And you aggregate information when you project this point of the 3 planes. One part of the information is. And we decide to produce the multiplane NeRF. Multiplane NeRF is constructed in this way that we take these existing images and say that it's the part of neural network, but it is not trainable. So it's fixed. And we train only the element and we aggregate the information. So here we train the 3 planes, and here we get the 3 planes which are already given by the images which was used. That it works very nice. when you have the right and point, you project in on this this point. In NeRF model, you have the projection from this side, so it is easy to reverse this process. It's quite easy to implement, and this works very nice. And occurs that it is nice because this model has some generalizing properties. So in general, when you train your NeRF, you must train the model independently, the neural net independent for each model. This one. And here it is nice because you can train this model on, I don't know, 2,000 of elements. And when you only switch this part, so change the images existing for another existing images, this part is able to aggregate this information. It's okay. It's okay. You can train the model on cars, and it gives for the model some planes, and it is able to render it. And we are now in this. Moment. Of course, these elements are quite nice, but NeRF is able to produce proper elements. So our model is able to generalize, but these generalized 3D objects are not with the same quality as classical NeRF, and reviewers also have some problems. Okay.
Thank you. That's it.
I want to say one maybe. Okay. Because always when I finish my talk, I want to say a few words about current projects. So because most of people when finish the work, it's nice, we are ready to do this and everything is okay. But I always want to show something more. So what we're doing now and what we want to do in the next steps if someone wants to get the part of this project they are in progress. So we have already finished some projects, and the first project which we work with is that we are able to produce the face with mesh. Now we want to work with hands, because in a VR environment you see your hands, so it's quite easy. We have similar model like Flame dedicated for hands. We have data set of hands from different positions, and just prepared already to use, and we try to model it to produce the hands moving in VR. The second element is that we are able to produce a nice 3D object, as I showed in slides, but we want to force the gun to produce face which is correct with with existing face in general. So we would like to produce some mesh, because it is quite easy to find the mesh of the face without colors for 3D. So in general, we want to condition our model by the face and force our model to produce a gun which is correct with the face. We are in progress now, but if it's possible, you can change this parameters in Flame, and your NeRF produce your generator produce you a face which is correct with this face. So we want to condition our gun by Flame instead of training a single NeRF. We try to produce the dynamic NeRF. So we believe that if you have the image of your element in different times, so here I don't know, is the time 0, and here is the time 10 when your span is changing. We believe that our model will be able to learn not only the position of the element but also the time. So we would like to produce dynamic NeRF. For its NeRF, we believe that people use voxels, people use T-plane, people use multiplane. So what should we do next? We believe that point clouds. So we would like to produce point clouds with trainable vectors, similar here, and force the points to move in the 3D space and find in some way the the surface of the object. The project is nice. We have the first result, but unfortunately, we obtained some points which encode the empty space. So the points are not only on the surface of the object, but also in the empty space because we need some information about that. This very nice model. We are very close to do it, but still some generalization. People in most cases produce the 3D representation of neural network. We try to produce 2D representation of neural network. So our neural network gives only information on the sphere, which contains the object inside. And we try to force the model to produce the elements only on the sphere without any rendering, 3D rendering, so without any sampling here, and produce the elements thanks to such as
reduce the complexity of the model by far, right?
Yes, if it is possible to train it, we don't need to sample elements here, and thanks to it, it will work in real life. Yeah, in real time.
It should work in much faster, right? Yeah.
Yes, it should work much faster. And we believe that it is possible to do it because now we are in this moment that everything works on the image which was used to training, but it's quite hard to produce the new novel views because they are blurry. And we believe that is a problem with representation of the sphere.
Well, there's a general problem with NeRFs that they are blurry. I mean, even with the approaches, with the voxels, or you always run in the over-smoothing problem. That's at least.
Yeah, but in this moment, the quality is too low. But I believe that it is possible because I'm not sure that it is possible to produce 2D representation instead of 3D representation. It will be work as fast as possible because we don't need to sample. It's a very nice project, and we try to use visual transformer because we can take only the points from this element, so we can take the patches from this element, and thanks to it we can use transformer. I think that is quite a very nice project. I find some people for it after 2 months of fighting, they say that it's too hard. And now I'm looking for the next.
Are there any other published works on this?
Yes, there exists some elements. There exists some model which use visual transformer for NeRF, but in different way. In general, they produce some patches on. Yeah, and all patches goes.
Okay, all patches going.
Yeah, or some selected patches, yeah, without any projection.
Mm.
That's why I believe that this can also work. I'm not sure how the novelty of the project is because I don't have any deep knowledge about visual transformer, and I only for a few seconds look at the paper, which this is rational, but I believe that it is quite nice because thanks to this model, we can open some new path of our investigation in our team. So for me, it's quite important, quite important project. But I have a problem with person to find a person who is able to train visual transformer and also work with MAM. There exists some algorithm MAM for few-shot learning, and I try to use NeRF. It's quite hard to describe. Interval NeRF, it's idea to use interval arithmetic, which I talked about in previous slides, to NeRF. Thanks to it, when you cross the rise, you have interval some 3D cube, which has the same value. So, thanks to it, your point is not a point, but has some value.
Is that Kacper-Kania?
No, it's not with Kacper-Kania, but maybe Kacper-Kania do something similar. I don't know. And of course, we fight with video because video and the object is similar way. So we have X, Y, and Z for NeRF, and for video we have YT for the time. And that's all. Thanks a lot. If you are interested in the projects,
So thank you very much. Okay, thank you very much. That was an impressive talk. A lot of information. So, but it was very interesting, and I think now we are open for questions. Probably hard to remember. Yeah. I could have notes. I didn't.
from my knowledge, hypernetwork long to train, and NeRFs always also take long to train. So it's like this combination super demanding of computation.
To answer this question, you should transfer two things. So most of the team all over the world combine NeRF with GANs, autoencoders, diffusion model, and in general, it is quite hard to train on our equipment now. So it is important. Yes, it is important. This thanks to it, you can publish a star conference. Yes, you can. It is. Do we have enough power to train it? No, we don't have. But in my opinion, it is possible to fine tune the existing, and we try to it even for diffusion. Yeah, and the second part of that for me, I believe that NeRFs has some problems in the fundamentals of the NeRFs, of how to sample elements of the array, how to produce the new views, and a lot of things is able to do on the one single NeRF, as multiplane NeRF, mesh NeRF, flame NeRF, OVD point cloud NeRF, interval arithmetic NeRF, and it is easy to train. I don't know, for a few hours you are able.
So, you got programs of the base NeRF, and those
base NeRF, yes, base NeRF, it means that this is base NeRF because for one element. This is base NeRF because it is trained for one object. This is base NeRF, this is base NeRF, and this is not the base NeRF because you have the GAN which produces NeRF. So during training, you must produce the NeRFs.
I think the answer should be NeRFs is just a subset of the implicit neural representations which encode the signal pointwise, and that should be actually the point of interest because NeRF is just one example where you encode it from images by registered images in space. But you can use SDFs, or you can use other things. And depending on what you want, I think it can be advantages in that. The problem is like NeRF is but hypernetworks are, I think, a great way to generate them automatically, right? That's it.
Yeah, we also work with similar way to produce the movie because when you be present in implicit way the video, it can work in similar way. We have similar project with voice, but it's not connected with the 3 points. So I want to say about this project, but if you know, I can show some project with sound and with which works in similar way.
But I'm not really sure if this question was answered. So how much more expensive it would be to pay now?
Okay, so here this project is in this project I have 3 people. One is the PhD student, one is a master student, but it's very good. Yeah, and I know. Yeah. And in general, I give him the access to the Perl grid, and I give him access to our architecture servers. And in general, when we finish the first implementation of the model, we train him for 1 week, and for 1 week we produce 1 app. I can show you how it looks like. It looks like that you have this part of place. And of course, we believe that the problem is not that we can solve partially the problem because the implementation of framework is not enough. It's not efficient. But so we believe that after the few iteration, we will be able to train it for a few days. Yeah.
I can understand that. When you compare your GAN
and so in general, it's something like that. Autoencoder-based architecture are able to produce 22 BSNR. Yeah, your GAN, our GAN, which I saw, produce PSMR 8. The state of the art.
Okay, on the
So-
sharp features.
Yeah.
Yeah, but I mean in terms of computational.
Autoencoders are better. From the computer,
Better, right?
it's better, it's easier to train, and we believe that it is. We believe that our GAN's not the only solution. I believe that you are able to produce some patch. We talk about it. That when your autoencoder-based architecture finish your training, yeah, and you have blue images, maybe it is possible to add here some patch. It only produce this more sharp. So maybe it is possible to stay in the autoencoder architecture and add some, I don't know, plugin here to produce sharp renders. Yeah.
Did you ever try the other activations for NeRFs or the
For NeRFs, yeah. For voice, for sounds, we use sirens.
But you tried silence.
For sound, we use
For sound,
for
okay.
sound we use
Yeah.
sirens. For NeRF, we use
And for the NeRF, but you use also the positional encoding.
yes, positional coding. Positional codings, but we didn't change the
This partially clear activation, the positional encoding. We have featured it.
in sound. We tried to do it because we have a lot of problem with sounds, and we look for the solution for the target network. But in NeRF, okay, so we didn't change anything.
So we essentially took the NeRFs.
Yeah. But maybe this is maybe it is possible to change something because we all the time change the hypernet. Autoencoder, GAN, MAM, or something. We all the time change. Maybe some idea is to change something here. But in all of our projects, here we have classical NeRF.
And in the autoencoder, this is like it's not a variation. That's
Yes, it is variable.
it's a variation.
So we are able to sample from.
You can sample.
Yes, we are able to sample.
You were using purely classical NeRF or this like this tri-plane?
We use the vanilla NeRF, so not instant NeRF or something like that. Of course, sometimes we use multiplane NeRF, which is produced by ourselves, but in all of the project we use classical vanilla NeRF, which was proposed in the original paper.
Okay, so you haven't tried those which you mentioned, like tri-plane representation, like padding, hash encoding.
And when there's a lot of work done on that.
Yes, we agree, but all the times where people change the representation with
You have to tune your generator and
in generative model, you need to produce all of this. How to produce these parts, you already know, and it gives SOTA. Yeah, so it is quite hard to work with this. Yeah, this is quite hard to produce by the generative model, so I believe it's not impossible. Yeah? So our idea is that you can work with that because it is easy to produce by hypernetwork approach, or you should to find something better than this. We try with this. It is not. I believe that it's not good idea, but we are already finished, so we have this. But in my point of view, here should be something more, which is more suitable for generative model. This gives SOTA. This I believe is possible and used.
You stick to the base formulation because it gives the good results, and you don't want to trade those good results with faster. You need something better for the hypernetwork. We have some experiments in our GANs and autoencoders. When you change the architecture, nothing is changed. Because when you train a single NeRF, you change the training time or inference time or something like that. When you put this architecture in GANs, most of the time is taken by GAN. And it is for computation time is not important which kind of representation you produce. But when your hypernetwork produces something, it's quite easy to produce the matrices. Here you have voxels, and in the most powerful voxel based, it's not a grid. In some elements, in some parts of it, there's thousands of hundreds of voxels. In some parts, you don't have anyone.
and you do it iteratively. Your architecture is not able to do it. Here, you produce planes of images. So if you take the SOTA of producing images, you obtain the SOTA from 3D object. And people use here diffusion, and when you try to train this diffusion, which is already given by the authors, the repository has thousands of stars, and it's from Google. You are not able to finish the training on this one epoch because this is a diffusion model with NeRF. There is any space to fight with or to be better than this solution because you don't have enough computation power, you don't have enough people, so it's impossible for me and for what. Yeah. So from the technical point of view of publishing, the idea is you can use here this or find something more. Here you are not able to produce anything because it's quite hard to fight with NVIDIA because you don't have enough people and stuff.
Yeah, I mean, I would like to thank you very much one more time once again. That was very impressive. A lot of information. Very interesting. I think this is still very impressive work, and I think there is a lot of avenues to go from. Thank you very much, and thank you for attending.